Greetings and welcome to Mr. Van Loo's poorly monetized, low-budget science channel. Do not click like, do not subscribe. Today we're talking about IB Physics topic D.1, gravitational fields. Learning objectives for this lesson will be to apply Newton's law of gravitation to the motion of an object in circular orbit about a point mass. Second, determine the resultant gravitational field strength due to two bodies. Third, describe Kepler's three laws of planetary motion. Finally, solve problems involving gravitational force, field strength, orbital speed, and orbital period. Okay, so here we have two masses, and as you can see, each of these masses is exerting an equal and opposite force on each other in accordance with Newton's third law. Additionally, we have one mass that appears to have a larger value than the other, and they're separated by this distance r, and r goes to the center of each of these masses. Okay, so all objects with masses are attracted to each other. You are gravitationally attracted to all the objects you're surrounded by, and in theory, all of the objects in the universe. The magnitude of this force of attraction is dependent on three factors. The first is that attractive force is proportional to the mass of each object. As mass increases, then attractive force should also increase. Two, inversely proportional to the square of the radius between the centers of mass. And third, dependent on a coefficient called the gravitational constant, which is called G in your data booklet. So here, putting it all together, gravitational force is equal to the gravitational constant times the product of our masses divided by the distance between those masses squared. And the gravitational constant is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, defining variables, just so it's very clear. We've already talked about all of those. There you go. Okay, next, gravitational field strength is the amount of gravitational force per unit mass acting on a small test mass placed at a point around an object. Okay, so we could place our test mass anywhere around here, and we'll talk about that a bit more in a second. But first, let's look at Newton's second law. From Newton's second law, we know that gravitational acceleration will be equal to force divided by mass. So this does explain the unit you may have seen for gravitational acceleration, Newton per kilogram, which is exactly equal to meter per second squared. You can break this down using algebra if you'd like. Okay, so we also know that gravitational force is given by this equation, so we can combine these two equations, and that looks like this. Using substitution, we put these two together, and we can simplify gravitational attraction to the gravitational constant times mass of our large object divided by radius squared. Notice that the mass of our smaller body, or test mass, is going to cancel out, so that's convenient. This is a little bit different than what is in the IB Physics data booklet, but not much. You'll be able to spot it. Okay, so these gravitational fields are depicted as these radial vector lines surrounding an object with mass. And the lines just show, the arrows specifically show the direction of force that a test mass will feel if you place it anywhere around this object. Okay, so we can see that the force is going to be attractive. If we zoom in on our circle, we'll find that the curvature is no longer visible, but our field lines are still perpendicular to the surface. So one analogy you can think of is if you go out to a large field, football field, or soccer pitch, you will notice that it appears flat, but we know that the Earth is a globe, and in fact, that flatness is kind of an illusion. Okay, if you drop a ball, it will fall straight down perpendicular to the surface. All right, velocities of objects in orbit. I would like you to find a general equation for orbital velocity. You will need to look at a previous lesson involving centripetal force. Okay, so you can pause the video here for a second if you want and go ahead and find this. I will show you how to do it in a second. Okay, waiting. Okay, time to move on. So you probably, after pausing the video, started by equating gravitational and centripetal force, solving for velocity. And when we look here at the two equations, this is centripetal force, this is our gravitational force. What we will notice is that our m cancels out immediately, and one of our r's cancels out, leaving the other one intact. So doing very little algebra, we get to this convenient formula in which velocity squared is equal to the gravitational constant times the mass of our large body divided by radius. And finally, we apply a square root to both sides, and we get this equation for orbital velocity. Okay, very convenient. So what is the relationship between velocity and distance? Well, what we should find is that velocity is proportional to 1 divided by our orbital distance. And the reason for that is because g and m are both constant. As distance increases, our velocity will decrease. And if we slide over here, we can see very quickly in Desmos what that looks like. So on this axis, we would have gravitational acceleration, and on this axis, we'll have distance. I put this together quickly, so it's not well labeled. Sorry about that. We're ignoring the constant. We just want to see the shape of the graph. So as our distance increases on the horizontal axis, you can see that our velocity gets smaller and smaller and smaller. When we're close to our object with mass, we find that our velocity is much larger. Okay, so there you go. So now period of the objects in orbit have a relationship to velocity, of course, and we know that velocity squared is equal to gravitational constant times the mass of the object, large object, divided by r. And we know that we can substitute velocity for 2 pi r divided by t. This is the circumference of our orbit, so the total distance of our single orbit, and this is the amount of time required for one orbit. Okay, so we distribute this square, and now we get this equation, and we only need to solve for t squared, and that will look like this. So we get the period of one orbit equal to 2 pi times the square root of the distance between objects cubed divided by the gravitational constant times mass. Okay, we could speed this up slightly if we know our velocity and we know our radius just by using this equation. Okay, so this then brings us to Kepler's laws of planetary motion, and we're going to come back to this equation specifically when we look at these, but hold that thought. So Johannes Kepler formulated the planetary laws by doing a bunch of number crunching of data collected by Tycho Brahe, who was a very wealthy man who would have fancy parties and then go out onto the roof of his castle or whatever and look at the stars and very, very carefully note their position and time and so forth. So this took a lot of years, and this is a pretty good example of an experimental physicist, Brahe, and a theoretical physicist, Johannes Kepler, where Brahe collected the data and then Kepler crunched the numbers. So Kepler's analysis results in these 3 laws. And we'll look at these in detail here in a second, but here they all are in one nice infographic that I got from Wikimedia Commons. I'll have a source for that at the end. So, first law, planetary orbits are elliptical with the sun located at one foci. Okay, so eccentricity is a property of our ellipses, and it's a coefficient ranging from a value of 0 to 1. So eccentricity of 0 is a circle, and most of our planetary orbits, including Earth's, will have a very small value for eccentricity, so close to circular orbits. As a result of this, we can model most paths, orbital paths, using circles, and that's fine. So here's the sun at one locus, or loci rather, and over on the other side we have another loci, if you know about ellipses and their construction, but we don't really deal with that in terms of the orbital mechanics, at least not at the IB physics level. Here we have a planet in a very elliptical orbit. This orbit probably is more similar to a comet than a planet. As we've already stated, most of our planetary orbits have small eccentricity. Okay, second law of planetary motion is this. An object on an elliptical path will sweep through the same area inside the ellipse in a given period of time. So there's a direct consequence of this, and that is that the velocity of the object increases as it approaches the foci within the gravitational well. Did I call that loci earlier? I did. Oops. Okay, so in the case of planets, stars will be at the foci, as we've already discussed. Here's our foci. Here's our other one over here, which we mostly ignore. Note that at this distant foci, when our bodies are closest to it, they have their slowest orbital velocity. Okay, as they get closer and closer and closer to the other foci where we have the gravitational well, their velocity increases. So that is a direct consequence of these equal areas in equal time. Large velocity, small velocity. Okay, third law is that the square of the period of the orbit will be proportional to the cube of the length of the semi-major axis. That sounds annoyingly complicated, but let's make it simple. So here's our diagram. This is the semi-major axis. Again, it's the distance from the center of the ellipse to the furthest distance in either direction, doesn't matter. And the period, t, the amount of time required for one full rotation about this ellipse, is proportional to this distance cubed. So t squared is proportional to this distance cubed. So we've already defined that. You will recall this formula from our previous slide, in which period squared is still proportional to radius cubed. So if our eccentricity is 0 and we have a perfect circle, this relationship still stands. Okay, that's it. Here are the sources. I used the Oxford IB Physics textbook. It's a course companion. And here is the image I used for Kepler's law. Very convenient. I use Google Slides, LaTeX, Desmos.com, and Adobe Illustrator. And finally, do not click like, do not subscribe. Just have a really great day.